So what I was hoping to do today is just look briefly at the gamma, beta functions and Frobenius method. So I want to cover the highlights. I won't do too many examples because I'll do one long one of Frobenius. It's the main plan. So so chapter 2, so which is what we're going to start looking at in this class, is looking at, to begin with, just lots of different functions. So we've seen polynomials, and we've seen a few special transcendental functions, namely trigonometry, exponential, and the inverses of all of those, inverse trig and logarithms. And so, but there's lots of other functions that are useful from time to time. And so we're going to look at a few of them. So one of the ones is the gamma function. This is the gamma function. So gamma x. Now it's good just to show where it comes from. So if you have an integer, so if n is an integer, and let's make it greater or equal to 0, then gamma of n plus 1 is equal to n factorial. So that's the basic idea. So the gamma function really is just a factorial function, generalized so that it's defined for as many values as you can possibly have essentially. So for our purposes, we can try to extend the definition to as many real numbers as we can. And so a key relationship, if it's got to match this one here, is that the gamma of x plus 1 is equal to x gamma x. That's a sort of key property. So therefore you get this sort of that's a sort of factorial property coming up. So that's an important one. So, and if you want to work at the gamma value of any of really large x or really negative x's, then you use this sort of property, either going forwards or backwards, one or the other, to get it into a nice range. And then there's tables of values for where you need it, if you do need those sort of things. So you can use this to get special cases. Another special case, which is worthwhile emphasizing, is the gamma of a half is the square root of pi. And that's useful from time to time because basically it gives you some sense of the factorial of, say, minus a half sort of idea. But you get factorials of other fractions, as half fractions that way as well. So that's a sort of the key sort of properties of the gamma functions. Okay, well, how is it actually defined? So it's really defined in a few different ways. It's easy to define it as an integral. So the integral from 0 to infinity of e to the minus t to the x minus 1 dt. Now, this particular definition only works if x is positive. Now, you can define the gamma function for negative x's, just using this relationship at the top here. It doesn't work for real numbers, negative integers. Otherwise, it's fine. So that's the main definition. So gamma, as I said, it's an analytic continuation of the factorial function, effectively. And there's a +1 difference here for some historical reasons, really. And it's used for that sort of purpose. So we'll see it later on when we do Laplace transforms. When otherwise you'd expect a factorial, you get the gamma function cropping up instead. I mean, we see those sort of things when we do it later. Also, it's useful in its own right for stats. So we see it when you're looking at the gamma distribution in stats, etc. So there's some various things. So although that's the main integral, just some applications that we'll see for it is if you try and integrate other sorts of things. So if you got e to the minus to a, z to the k, for example, z to the l, dz. So you've got other sorts of integrals which look like that. You got an exponential of a polynomial and a polynomial to some various power. Those sorts of things. Then if you let if you simplify this power, so let the a z to the k just be a simplified power t, and then simplify it down, then you can reduce this sort of integral to be something close to an integral for a gamma distribution, and therefore rewrite this in terms of the gamma function. So you can use it for lots of them. So if the limits are right, works really beautifully. If the limits aren't quite right, you get almost a gamma function, and that would be called an incomplete gamma function, which are also useful. The formulas for which are getting even harder to work with. So we won't touch that, but the technique of trying to simplify these down into something looking like a gamma integral is sort of an important skill. So let's just do one example for that, just to give you an idea. So say the integral, say from 0 to infinity of e to the minus 3z to the 4 z dz. So again, just like I said before, when you've got e to some power of polynomial, let t be what's in the polynomial. But what we would like it to be is we want a negative power. So we want to die off, so the negatives need to stay there. And so taking differentials, dt is equal to 12z cubed dz. And so making, there's a z dz there. So let's go, so z dz, making that the subject, is going to be equal to dt on 12z squared. And then we can rearrange this equation. So z squared then, this equation will be equal to the square root of t on 3, making z squared. So putting all these in terms of t's, this would be so root 3 on 12, and it'd be 1 on root t, so say t to the minus half dt. If you look at the limits, so when t is 0, so when z is 0, t will be 0. When z is infinity, t is infinity. And so the integral, the limits don't change. It's still 0 to infinity. We can e to the minus t by construction, and the z dz becomes root 3 on 12 t to the minus a half dt. And for some reason, whoever decided to define this gamma function, which is probably Euler, I can't remember who did it really actually, he did lots of them, is to have the off by 1. And so what we normally do is, instead of having minus a half, express it as a number, so a half, minus 1. And when you go to the sort of form, when you have this particular integral here, then basically the answer is going to be the gamma function of whatever this power is, so half. And as I said before, gamma of a half is one of these special values, and it's equal to square root of pi. So that's an example of how to use the gamma function to solve various other integrals, essentially. And so other sorts of ones you can do is, if you got integrals, say 0 to 1, things involving minus log u of some power, and say u to some power, then letting, say, t is equal to minus log u will end up generating things like the gamma function. Oh yeah, a constant times that normally. So that's a useful trick. So you've got minus log u to the first power. Now, if m's an even integer, for example, the minus sign might drop, might disappear entirely. But if it's another fraction like a half or a third or odd integer, then it's important to remember it's there. So that's some other ones. And if the limits weren't 0 to 1, then you get incomplete gammas. So as I said, the gamma distribution really is just an extension of factorials. And so really what we want to do is we want to define beta functions as extensions to combinations. So we talk about n choose k as being a number of ways of choosing k things from n, and normally that's defined by a bunch of factorials, right? So n factorial n minus k factorial k factorial. So what we want to do is we want to try to extend this sort of idea, and that's what the beta function does for us. So the beta function, and again, so we'll call it say x and y. We define it by an integral. So it's integral from 0 to 1 of t to the power of x minus 1, 1 minus t, power of y minus 1. And in this sort of thing, it's actually equal to, we'll call the definition. So we'll define it to be this integral, and this integral ends up reducing down to the gamma function of x. Oops. Times the gamma function of y over the gamma of x plus y, which you can see is it's closely related to this. So you can see a combination here is the factorial of a sum of two things over the factorial of the individual part. So really, the beta function here is related to the flip or the reciprocal. So the combination sort of function is related to the reciprocal of the beta function. So there's a connection between the two. And so if you looked at so essentially if you put a binomial coefficient in front of it, then you end up getting something like unity. It's roughly the idea. That's why there's reciprocals there. So again, there's this off by one issue here, which is the thing that I always think looks unusual, at least personally, and therefore that's the part I tend to forget. Just to remember those parts here. So the beta function really is, you've got any sort of integral, just a way to simplify it down. And as you can see, that really it's just an extenuation of this, or these are the binomial coefficients, is the idea, to non-integers. That's a really important thing of doing it. So it's an analytic continuation, and it doesn't apply just to integers and not just to real numbers. It actually works to complex numbers too if you do it properly. And so just like before, you can use this to solve a whole stream of integrals. So if you've got integral of various limits of 1 minus any old function here at all, so f of u, say, to the, put it just k in general, and something at the front, then you can sometimes reduce these to beta functions. So it works. So if f of u is, say, a polynomial, and the front's a polynomial, then letting t is equal to fu works nicely, or if f of u is an exponential and the front is some another exponential, letting t be that exponential is often a good way. And as long as the limits are nice, then you get the full beta function. If the limits aren't so good, then you get an incomplete beta. So you work with what you got. So in this subject, I don't want to look at incomplete beta functions. We'll just look at complete gammas, complete betas. Let's make it, there's enough to learn as it is. And so the beta function is used as a first glance as some connection with the binomial coefficients more generalized. In stats, you see this in terms of the beta function, which is used in Bayes analysis in trying to understand proportions. So if you're trying to have if you have a belief, if you have a belief of how many people are going to win the next election, then you can model that using a beta function. So you have these things cropping up all the time. That's quite an important thing you'd see. So if you do Bayes analysis, so that's sort of where certain things fits for this. So that's just two functions. So the gamma extension of factorial, and the beta, which is an extension of the binomial coefficients. So both important functions, and you see we'll certainly see the gamma function crop up later when we do Laplace transforms, etc. So there's an error function which is related to those, and so they sort of a family of functions that are closely related to each other. So that's the first bit, and so in chapter 2 it seems like just a collection of them. There are lots of other functions you might want to consider, and the way to look at the rest of them really boil down to looking at series solutions to differential equations. That's what the rest of them sort of boil down to. And so a key method to work them out is called Frobenius method, which I'll mention in a second. But just to give you a framework to see how it all fits together, that we'll get quite a few, as it mentions at the end of the chapter, that most of these things can be unified by what's called the Sturm-Liouville theory, which is a way of looking at a family of solutions to a family of differential equations, and seeing some special relationships between them. So the functions end up being have a nice connection. So in particular, they end up being an orthogonal basis for some vector space. And so that's really handy. So that's where we're heading towards. And so there's lots of different ways, lots of different families of functions that can arise due to Sturm-Liouville theory. We look at a few. And in order to see how you can handle in general, we're looking at just a few case examples. So the beta, the Bessel's functions is one particular one. So I'm not going to mention any of those details today. I just look at the main method. So this is Frobenius method. So this is certainly an important tool to work it out. So before we do that, let's take a step back and just to give you a sense of how it works. So what we want to do is commonly we want to solve things like px y double dash, and this is when I do y double dash derivative respect to x here, plus qx y dash plus rx y, in general equals to another function of x, or it could be 0. So what I'm doing here is I'm looking at how to solve second order differential equation where the coefficients are not constant anymore. So we've looked at chapter 1, this sort of thing, where we had constant coefficients, and we solve lots of them with constant coefficients. But now we're looking at variable ones and how you handle that situation. And the answer is, in special cases, you can resolve it down nicely, but often it gets really tricky very quick. It gets tricky very quickly. And so the way to handle this is try to go, well, although we can't find exact answers, using power series is a good idea. So power series is a good way of handling that. Well, I'll say sort of. So I need to qualify that. So if you can write down a power series solution for this, then power series only work if the function's called analytic. And so these, if you've done complex analysis, MTH418, you would have seen some of these words in the full generality. But so it's all come back to complex analysis. But essentially, in terms of real numbers, a power series is defined nicely so long as a function is infinitely differentiable on a certain interval for real numbers, or on a certain open set for complex numbers. So you really got to find all derivatives, and therefore if there's any singularities at all, power series stuff up. And so power series work nicely. So these power series, which is pretty much saying let y is equal to the sum of terms long as a to the n, x to the n. That's pretty much what a power series looks like. N greater equals 0. So they work nicely. If px is not 0 about the point you're trying to take the power series for. So in general, the power series really is expanding about a certain point. So px naught. for simplicity, we will always consider x naught being 0 in the examples we do. It's hard enough as it is. It's enough work as it is. So we'll just consider x naught as sort of an example point. So x naught being 0 being the key point. So this is the sort of power series. So long as the point you're trying to work it out, so long as this function here is not 0, and I should say a few more things, and assuming that qx naught and rx naught are well defined, that actually all these coefficients are defined, and the top one is not 0, then it works nicely. In that particular case, x naught's called an ordinary point, and your power series work quite nicely. But sometimes that doesn't happen, right? So let's just mention an example of where this fails. I did write it down here somewhere. What did I? So here's a differential equation. You can see it's got variable coefficients here, and again I've written it in such a way so that all the functions are at least analytic, i.e. they're infinitely differentiable essentially. So you can clear the fractions. So if there is any fractions, you can just clear the fractions out, and so we can assume each of these coefficients are at least analytic, i.e. differentiable everywhere. But you can see that this leading one here is 0 sometimes. So in particular, it's 0 when x equals 0. And so this one actually fails for the power series method. So if you did the power series about x equals 1 or x equals 2, it's fine actually, it will give you a reasonable answer. But when x equals 0, some funny things happen. So if you just plug it in, so if you plug in x equals 0, then there's no way of working out what the double derivative is. And so if you think about how to solve things numerically, then you don't have any information about what the double derivative of x equals 0, and it's hard to push through it. So there's some sort of singularity there. Now, so you've got a problem, so you have to do something else to handle it, and that's what we'll focus on. So again, it doesn't always work. So if we divide everything by x squared for the moment, not that you need to do that, but explicitly, but it's worthwhile just doing it here because it helps understand what's happening. So if I notice some simplifications happening, I notice that in this case, an x cancels out, so it's just 6 on x and 6 minus x squared on x squared. So they're various coefficients. So when you divide by x squared, you can see that, well, although the front here is nice, that these coefficients here aren't actually well defined at x. And that's really what the problem is here, that there's a singularity at x equals 0 because the coefficients aren't well defined there, essentially. Now, if they're really badly undefined, then the function might be really badly defined at x equals 0. There's just no point trying to work out what it is around it. But in some cases, you can recover a nice answer. So broadly speaking, is if the highest power at the bottom of here after simplification is just power of 1 or less than that. So yeah, so if there's no on x at all, or if it's just x on x to 1 at the most, that's why it's called a polar of order 1. That's fancy way of saying polar of most order 1. And if the highest power on the bottom here is an x squared, so most polar of order 2, then you can recover a solution, and it would be singular at x equals 0, but you still can recover it, and that's okay. In that particular case, you can use Frobenius's method. So, and so Frobenius method then allows you to write down a series solution for it. So that's the bigger picture. Let's try to write down some details. So you got what I had before. So your px y double dash plus qx y dash plus rx y. So again, let's just do the homogeneous case. then what we're going to do is we want to check if when you do QX on PX, that you're going to get a pole of at most order 1. And so if you multiply it, and again, we're just going to consider x equals 0 as the only case we'll do, but you can do x minus x naught in general. So if you want to multiply by x, then pretty much we're assuming that we're going to get, it's going to be well defined then. So if you take the limit as x approaches 0, this ought to be finite for it to work nicely. And again, if you take the limit, if you do the Rx on the Px, again, we want it to be an order at most x squared. So if you multiply x squared, again, when you take the limit, we ought to get something finite. So these two conditions here just guarantee that loss property, as I said. So as you can see in this example we've got here, so that's the QX and the Q on P already. So if you multiply that by X, so we did the P, what was here, Q on P, times by X, then that's going to be just what's on the top of the fraction here, just the 6. And if we take the limit of that, as X goes to 0, well, you just get 6. And you can see that's a finite number, so that's okay. So just showing it's working here. This one here, you got 6. So you've got the R on P times by X squared. As you can see, it's just the top of the fraction here. So if you take the limit as X goes to this point in question, so the place where you got the singularity, you should get 6. So these expressions both go to 6. They're both finite. So it will tell you that Frobenius method is actually going to work in this circumstance. These are useful. So let's give some we'll call it B and C. Give some labels to them. We'll see where they crop up later. Different way of doing it. So if you got both of those conditions, then a solution is Y is a power series like before. So A to the N, X to the N. And again, we'll just make it X equals 0 to make it easier for ourselves. Except that we want to cover the singularity. So the way to get a singularity is putting an X to the R here, where R is going to be some other thing. So it could be a fraction, could be negative, could be positive too for that matter. So that's what sort of thing we're looking for. Now, you can muck things around a bit. So just to make it easy, just to avoid ambiguity, it's easiest to write, just to find A naught, which is the bottom term, to be not 0. And basically the X to the R term just gets all the other power off that way. So that's just a convenience thing, makes it easy to define. So that's the sort of solution we're going to looking for. So for example, you could write, you could factorize X to the R in, of course, so it's X to the N plus R. And so the first term is A naught, X to the R. Next term is A1, X to the 1 plus R, etc. So I'm just making sure that the bottom term here really is just a constant times X to the R. That's why I want to make A naught not 0. And in particular, what we'll commonly do is, because this will form a fundamental solution, it won't form the whole general solution, just a fundamental solution, then commonly, we'll often let A naught be 1 when doing some various calculations, just to make things easy to work with. That would produce a fundamental solution for us. So that produces one of them. So it's second order, so we actually expect 2 different fundamental solutions out there. And so that will covers one. How do you get the other one out? In nice cases, the other solution will look exactly the same as that. It will have the same sort of form, just a different R. That's great. Doesn't always. So sometimes the second solution looks something similar to that, but has a logarithm terms in there under certain different circumstances. So and it does depend. So how do you work out various things? So how do you work out what the R is? How do you work out what the ADN is? That's big, important questions. So let's show you. And then we'll worry about how do you pull out the second solution when it may or may not be so easy to do. So this is big picture for the moment. So to work it all out, we could just sub it in. Let's look at we'll do an example up here. This is our example. If it lets me copy it. So this is the sort of solution I'm going to try. So y is just a0 xdn plus r. So what I want to do is I want to try to sub that into this expression here, right? And so what I need to do is I need to work out what the first derivative is of this expression. And so, take derivative, the n plus r drops down, x to the n plus r minus 1, y double dash means you take derivative second time, so another power dribbles down. Now, it's easy to lose sight of what's happening here from all the different operations. So all I'm doing, I want to sub in here. That's the big picture. So I'm just trying to sub in. So this is what my example expression is. I'm just going to take some derivatives and plug it in. So therefore, I need to know what y is done. I need to know what y dash and y double dash. So that's what I've got. Now, it's useful before I go to try to sub it all in one go. Is to go, what's going to happen if I multiply? We'll take the first term here, x squared times by y double dash, for example. And then just do term by term. Let's try not get carried away. But although we have to do it a step at a time, we really are just subbing in. And so once we sub it all in, we'll end up getting a series over here is equal to 0. And those will both equate so long as all the coefficients are 0. That's the basic idea. So the coefficient of the bottom term will give you what's called the auxiliary equation, which is really nice. And then the coefficient of the general term will give you what's called a recurrence relationship. So those are really important. So there's a pattern very quickly. So the first few terms are special cases, and there's a general thing. So that's the big picture. Let's look at the details. So how do you do it? I want to look at each at a time. So if you multiply x by x squared, essentially it's going to add 2 to all the power. So it's going to look almost the same thing. It's a0 and plus r, etc. X to the n plus and the minus 2 and the plus 2 cancel out, which is good. And you can do the same sort of thing to the, if you multiply x y dash is the same sort of idea. That's why I suppose my ditto mark. So all that's doing is it's just going, adding 1 to the power, so the minus 1 and the plus 1 cancel out. So they look pretty nice. And I mean, what I could do is I could chuck a, so let's do some. So if I did a 6 of them, there'd be 6 in here, etc. If I got 6 times by y, that's the other term I want. So 6 times by y would be 6 times that. That gives you the 6y. So the other term we have to really worry about is the x squared, what y looks like. So that'd be summing n equals 0 of a to the n. Let's get all these things right here. A to the n of x to the n plus r, and we're getting add 2. So let's just look at the terms that we've reduced. So they've got 6y, and you can see you've got powers of, and we're summing over powers of x, the n plus r. These are the other terms that we're interested in n plus r, n plus r. So you can see all the other ones are really summing up where the general term is n plus r. And so in order to match the series, make the series all match up neatly, we need to make sure that the power here looks the same. It doesn't at the moment. So we've been fortunate most of them line up. This one doesn't, so we need to fix it up. So this is sort of the detail. So in order to make sure them all match up really neatly, this is one of the things that we need to do. So that we can just compact in one nice thing. But we really are subbing in collecting like terms. So what I want to do is I really want to make this thing look like n plus r. So what I'm going to do is I'm going to let, well, these that are plus r part, that's the same. So I'm going to let n plus 2 just be equal to some new index. Let's call it n dash, just a new sort of n, essentially. And so therefore the sum, well, if n is starting at 0, going from 0, 1, 2, 3, 4, then n plus 2 would be starting at 2. So 2, 3, 4, etc. So n is greater or equal to 2. N here would be my new index minus 2. And x to the n plus 2 would be x to my new index plus r. So the purpose of redoing that is that all the different n plus r's all now match up. And so now I can chuck them all together. And again, what I'm actually looking for is a minus of this. So minus that term. But you can say all match up. So now we can all add them up. So when we add them all up, when you can see looking at all the different terms we're trying to add up, all the indexes, some of them start at 0, one of them starts at 2. So but when this counter, so whatever it is, that gets to 2, all the terms are involved. So that was sort of the general sort of term. When n is 0 or 1, you get this bottom case missing out. And so you get those two special cases. So let's just put the next page. So if you chuck them all together, so put subbing in this time. So put them all together, you get, so when n is greater or equal to 2, then you're getting x n plus r, and you're getting all the terms cropping up. And so I'm just gonna, you have to trust me, I guess, that I'm putting all together. So you'd get the bit which corresponds to the x squared y dash term, which is 80n n plus r minus 1. So that thing here corresponds to the x squared y double dash. That's where that one came from. And then you have then there's the 6x y dash. So that's the 6 a to the n n plus r. And then there was the plus 6 y, so that'd be 6 a to the n, and you have minus 6, so minus x squared y, which was minus a to the n minus 2. That's where they all sort of come from. So if you just flick back, so the terms I'm looking at was, there's the 6, in order I should say, the ones I did so was, firstly I had that sort of expression, then I had that sort of expression, then I had that one, and then lastly I had the minus 80 and minus 2. So that's what it looks like in general. So I just put them all together. So then I have the special cases. This would be, and let's put in brackets here, this is the n equals 1 case, and the other special case, n equals 0. So these are the sort of bottom ones. And they look almost the same. So it's just going to be x to the, in this case, 1 plus r, next to 0 plus r. and I could write down almost the same way. So they're the same sort of things. The one difference, so let's put dot 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 for the moment. The difference between the general term and the other one is that this very bottom one here started at 2. So any terms it produces won't be in this special cases, so they'll be missing. So I won't worry about this one in the middle for the moment, but I'll do the bottom one. So this would be A naught 0 plus R 0 plus R minus 1 plus 6 A naught 0 plus R plus 6 A to the naught. And as I said, the A, the n minus 2, well, doesn't really make sense, so that just doesn't come up at all. Let's put a big bracket here for all of them. So all I've done is subbed in. And remember, all this expression is equal to 0. So I've just subbed in the left-hand side and the right-hand side still is 0. So what the Frobenius method is doing. So what happens is if you look at the bottom, the very bottom case, so the n equals 0 case, what this will do is recovers the what's called the auxiliary equation. The one which comes up in general, the one at the top, this would end up producing the recurrence relation. This is the end up producing the auxiliary equation, which I'll show you in a second. The ones in the middle, so there'll be one more here, do produce other useful things as well, I might add. In some cases, that may not exist. They might be just the auxiliary and then their recurrent relationship, which might be 2 options. In more annoying cases, which is what this one is, you get other things cropping up. So let's look at this bottom one, and then we'll see some general ways of doing it. So if you look at this bottom one here, you can see there's A to naught in every single term. That's sort of how it always happens. So it's A naught, and it's R minus 1 plus 6R plus 6. And again, since these got to both be equal, that's got to be equal to 0. Now, just some pointers, other ways of reconstructing this thing here. That 6 is the B I defined earlier, and this 6 is the C I defined earlier. So if we flip back ages, that's the B and the C from before. So essentially, they really are that's the called B for the moment, and C is this one here. So these are the limits that you're doing to check that it actually that the singularity point here is going to be good enough to be able to work for the method to work. So for them to be regular singular points essentially. So those things that you've so in order to check it's going to work, you will have to have produced them already probably, and so they do get recovered. So although I've tipped the whole thing out, you can find these out other ways. Now that's sort of expression we want. Now for this to be equal, either A naught 0 or this other polynomial here in R is 0. Okay. So, but to make things nice, as I said, we tend to assume that we'll assume that A naught is non-zero, and commonly, so without loss of generality, we will just take A naught to be 1 even, make it a bit even easier. But in particular, just to make things work nicely, we're going to make A naught non-zero. That always is the case. And so what we end up producing then is you're getting R minus 1 plus 6R plus 6 equals 0. So this expression here, this polynomial, is called the auxiliary equation. And what will it be? It'll be just a polynomial in R. So since we've got order 2, it's a quadratic equation. And just a matter of solving it. So if you can solve, so therefore you factorize it out, so you're getting R squared plus 5R plus 6 equals 0. And so you're getting R plus 3 R plus 2 equals 0. So that's the auxiliary equation in this case. So the solutions for this, which is R equals -2, -3. So let's just take a pause, go back to what the method is again. So if you've got a polynomial with variable, so you've got a differential equation where the coefficients are variable, and you're trying to work out a series solution for this where the coefficient of y double dash here has got, is 0 at x equals 0. You're trying to work out a series solution at x equals 0, and you've got some nice conditions happening. Then we know the solution's going to look like this over here. So therefore the answer is, well, what is the solution going to be? That's what Frobenius method is trying to answer. So to do that, you need to know what R is, and you need to know what the A to the N is. You need to do both of them. So to work out the R, you write down the auxiliary equation, like I just showed a second ago, and solve it for R. So what we've done in this case, we've shown that R is either -2 or -3. So they're the two different cases. So if things work nicely for you, then if you do them both separately, so if you do the R equals -2 case, R equals -3 case, for each of them separately work out what the ADNs is, which I'll do in a second, then they'll recover both fundamental solutions and bang, fantastic, got your answer. Now, if the two values you get differ by something which is not an integer, works perfectly well, great. If the two values are the same, so it's double root, or if they differ by an integer, then you might get log terms cropping up instead. In this case here, you can see these differ by an integer, they differ by 1. And so it's not clear at first glance if they're going to be log terms or not. And so we do have to be wary of that. So if for simple cases, you could just try them both and just hope that the log terms aren't necessary. The other way is to do reduction of order, which is what I'll try to do. I'll try to do quickly just myself before I get to it. So that's work. So that shows you what R given for R values. So once you know what the R values are, you just pick one of them, just one at a time, and then you work. Then from that, then you try to work out what all the different ADNs are. So as I said, we're trying to find this thing here. So we now found an R value. So R equals say -2, for example. Now we need to find what all the ADNs are. And the way to do that is to use this recurrent relationship in general and also in any special cases. So I should write down what these special cases are explicitly. So this is what it is in general. So each of these coefficients must be equal to 0, right? But we're going to let R equals -2 to make things easier. So I actually only write down the. So if you let R equals -2 in this top expression here, this coefficient, so A to the N plus R, which in this case -2, N plus R -1, so N -3, plus 6 A to the N plus R, plus 6 A to the N minus A to the N -2 equals 0. So that's what I just subbed in R equals 2, and I just calculated that particular coefficient equal to 0, because that's what there's a big 0 at the end here. And this allows me to work out, if I know what A to the N -2 was, this allows me to work out what the next term up is. So it tells you what some terms are in terms of earlier ones. So you can simplify this down a bit. So if you put all those together, you're getting A to the N outside of N plus 1 times by N. And then you've got to chuck the A to the N -2 on the other side, because A to the N -2. So it simplifies down quite a bit in this case. So a little bit of effort. And so you can see that A to the N is equal to A N -2 on N plus 1 times by N. So if you know what two terms of 4 was, you can work the next one up. So for example, when we've defined A0 to be just 1, that's what we defined it to be, and so A2 then, plug into this micro-recurrence relationship would be A0 on 2 plus 1, so 3 times by 2, and that's going to be 1. 3 times 2 is 6. I'll write it as 3 factorial, just because you know what the pattern's going to be. And so then I could do it at a to the 4 as well. So a to the 4, plug into my expression here would be a to the 215 times by 4, which is 1 and 3 factorial times by divided by 5 divided by 4, which after simplification becomes 1 and 5 factorial, etc. And so if you write down the first few terms, you probably can sometimes see a pattern. So you probably can guess from that. If you've got a to the any even number, you end up getting 1 on 2 to the n1 plus 1 factorial. That sort of thing that happens. So you go, well, and that's how you use recurrence relationships. So the question that you might ask is, well, how do you work what A1 is? Well, in simple cases, the recurrence relationship would produce all of them for you. The thing I haven't mentioned is this bottom case here. So this is the bit I've missed out. So if you worked at what that term was explicitly, and subbed in r equals minus 2 into it, and then try to solve that equal to, and you get A1 times lots of other things, and try to solve for A1, that'll tell you what A1 is. I won't do that, but I'll just tell you what the answer is. So if you do that process, you'll find that A1 is 0. And then by extension, therefore, if you plug, if you try to do A3 into this expression, so A3 would be A1 times something or other, it's also 0. And so you quickly say that A for any odd number is 0. So putting it all together then, so one solution for this particular expression is y is equal to some n greater equal to 0 of an x to the n plus r, that's what I said. We now know what everything is. So if it was an odd term, they just disappear. So there's no point putting it in. If it's an odd term, if it's an odd term, they just disappear. So really just the even terms that sort of matter. And therefore, we might as well just sum it over m. So it's even terms. So it's x to the even plus r, which was minus 2. And all the coefficients for even terms is 1 over 2m plus 1 factorial. So that's what the answer is in general. And so if you, let's write down the first few terms. So if you plug m equals 0, getting 1 over x squared. Then if you plug m equals 1 into here, so you need plus, so m equals 1 gives you 1 over 3 factorial plus x squared over 5 factorial, etc. So that's what the first few terms look like. In case you're wondering what this function looks like, if I take the 1 over x squared out, as a matter of fact, if I take it whole 1 over x cubed out, the reason why I want to do that to go make it a plus 1, so just make those things match up. Then if you're doing summing of 1 over an odd factorial, if you're just summing over odd terms, that's what I've got here, just odd terms, where it's 1 over factorial, then this is a power series you might know. So it's just a normal Taylor series, about x equals 0. That ends up being sine, it's a hyperbolic sine of x, which you may or may not know. This gets mentioned in complex analysis, for example. So that's an actual solution. So you can see the solution, although we put it to the power series, sometimes they do reduce down to something a bit nicer. Now you could do the same process so with r equals -3, and you could repeat the process, and it'll give you another solution. So to give you another one, y is equal to the same sort of idea. It ends up getting cosh of x on x cubed. And there's a lot of work there, as I'm sure you can imagine. Same amount of work, really. And that gives you two solutions. Now, sometimes in this approach, the two methods they give you are linearly dependent upon each other, and that they are therefore not a fundamental set. And so you can do things like they're constant to double check if they really are independent, and therefore they do generate the whole solution space. That's one option. Another option is reduction of order. So let's see if I can tell you super quickly this idea of reduction of order. Okay. I'm out of time, so I'm just going to these are some notes I've got. So this is the idea of a reduction of order. So I'll just give it to really roughly for you. So if you know you've got one solution already, so y1, and in this case, the solution we had, just to make it concrete, we had sine of x over x cubed. That was our explicit solution. So we've got a closed form for it. Then this is a way of working out a second solution to this sort of differential equation. So just like when we use it, Frobenius method. And basically the idea is to let y, that's the variable we're trying to solve, be our solution. So sine x on x cubed times by some new variable z. Then if you plug that sort of this expression into the original dE, then you'll get z and z dashes and z double dash terms all cropping up. The good thing is all the z terms just disappear. They just vanish. You still get z dashes and z double dashes cropping up, and so you can just write them down. So you get that sort of expression in general. And we want to try to solve for z. That's really what we're trying to do. So you can see that z is equal to a constant is one solution, but we want to produce the other one. So some sort of other solution will give you what we want in general. That's sort of the idea. To try to solve for it, it's useful just to reduce the order. So let w be z dash, and it produces this sort of expression. So it's exactly the same as you can see, just replacing z double dash with z y dash, w dash, z dash by w. And so if you sort of followed that logic for this particular case, then you end up getting, so for this example, w dash is equal to, so minus 2 cosine sine w, I think it is. Yeah. So, and that's what you end up getting. So that's the sort of thing you're getting. So you can see you get the sine x's cropping up. You've had to take derivatives so many times, cosh is cropping up too. So that's the sort of expression you get in that case. Now, when you got this case, that is just a matter of solving it. And so this mentions how to solve it. And as you can see here, the way to do it when you got this sort of expression is you can just do it by separating. So it's just a separable differential equation. So this would be dw dx. So you separate it, so dw on w is equal to minus 2 cosh x and sin x. Dx. And so if you integrate this left-hand side, you're getting log of w. Absolute value signs in general, I'll leave them out. Let's put them back in, put them minus 2. If you notice here, the derivative of sin is cosh, and so we end up getting, whatever that is, log of the bottom. Plus some sort of constant. If you get rid of the exponentials, get rid of the absolute value signs, you can absorb it all on the constant. Then you're getting w is equal to, say, a constant. Let's make it minus a just for trickiness sake. So it's a constant anyhow, times by, we'll get out, sin squared x on, or 1 over, because it's power of minus 2. So w is minus a on sin x squared if you get rid of the logarithms. But w here, remember, is z dash. So z dash is this one. So basically I've reduced the order, produces a nice differential equation to solve, to separate it. Once I've separated it, then integrate a second time. So z would be just integrating this one. The integral of 1 over minus sin squared x is 1 over minus cosec or something like that squared. And so if you integrate that, you're getting cough. So this is hyperbolic cot. Now, just in case you're getting worried here, don't expect you to know all the different results about hyperbolic trigonometry. It's handy to do it quickly, but I'm not expecting you to memorizing it by any means. So if this was in terms of trigonometry, so cos and sine, yes, I expect you to handle it all. So if you go, I don't think I know that, that's fine. Don't feel bad. I don't expect to be able to reproduce it all. So you quickly said that z equals a cotangent x, but when you're integrating that, you have to another constant, so say plus b. And then lastly, as I said at the top here, our general solution y is equal to y1 times by z, so times by this expression here. So if you plug that in, you can see the plus b will just give you the b sin x on x cubed. So that's a solution we already knew about. If you plus a cot, hyperbolic cot times by hyperbolic sine, you end up getting hyperbolic cos or cosh plus and add them up. So that would be the general solution. And you can see the a and b makes it the full general solution that way. So that's the sort of idea of reduction order, which I did super quickly, admittedly. So that's the result in a nutshell. But I mean, you can do it. Don't have to remember any results to do it. If you really just let y is y1 times by z and plug in, it just falls. Things just simplify naturally for you. That's sort of how it works out. And that's useful sometimes. So, but that's certainly handy if you're going to get logarithmic terms cropping up by any means. So if there's going to be logs cropping up, which there wasn't in this case incidentally, that sort of reduction of order is very handy. If logs don't crop up, then the original approach of just Frobenius method of just doing a second time, which is what I hinted at the bottom here, is fine. So just a recap of Frobenius method, which I spent most of the time on. So the Frobenius method is a useful way of finding series solutions when you've got a ordinary differential equation with variable coefficients, so long as when you're looking at the power series about a singularity, and the singularity you're working out is nice enough. And what I really mean by that is so long as that the order of the poles and the various other terms aren't too big, essentially. And if it's nice enough, then you can find solutions of the form XER times by a normal power series, essentially. And so Frobenius method shows you, one, what the precise conditions required are. 2, how to find the auxiliary equation to find R is, and 3, how to then, given a certain RB, to find the power series next to it. That's the basic idea. So that's it. That's in a nutshell. And so Frobenius method is a really important algorithm. You need to make sure you get your head around it yourself, of course. There you go. Any questions you have? Lots to take in. And again, mostly it was doing more of a lecture today rather than anything else, because it was the beginning of the topic. Because I know everyone was busy doing their assignments recently. Okay. So something I did here, which is what your question is I subbed in to work what the first few terms are. So for nice cases, there are very nice patterns to all the coefficients. You can write them down. It's good to know and recognize if you can, but in not so nice cases, the pattern's awful or anything like that, or sometimes the function, at the end of the day, it's not so nice. So you need to be able to work out what the first two terms are. That's the only real requirement. And so the corresponding assignment question here, I'm pretty sure, just says work at the first few ones. So I mean the exact marking scheme says find the first 4 non-zero terms. That's how it says it. So that's sort of how I'm marking it. So I'm only expecting you to better work at the terms. I don't expect you to work at the pattern. But it's useful if you can. It's an add bonus rather than a requirement by any means. So for this for the assignment, I'll give them some hints. I mean, if you read the assignment, there's big enough hints to tell you what the pattern is anyhow. But in general, just work them out. And again, if you in practice, what are you going to use it for? Well, use this sort of method for a few things. One, to try to find these family solutions like Bessel's functions. So you're trying to understand them better. Other times you're just trying to use them to work out what's the answer. And now I've got all this thing here. What is the value of the function x equals 1? And you just want to sub it in and try to work it out. And therefore, for that purpose, all you need to know is what the coefficients are numerically. You don't really care about them, what a sort of function is for them, etc. But more of that's covered in 307, that sort of idea if necessary. Any other questions you've got? Okay, cool. So make sure you have practice yourself and read the notes. I mean, there's more examples which will hopefully be helpful for you. And so, if you want to see where logarithms crop up, so Bessel's functions certainly show you where the log terms crop up and sort of how you can handle that sort of situation where it's handy for it. But anyway, I'll see you next week. And thanks for